All right, hey, beautiful class. We're going to start on chapter 4. Chapter 4 is really long and packed full of information, so we'll get about halfway through it. All right, so brief review of nomenclature we know so far. So remember, we know those prefixes and we know the suffixes if it's got like an ein, or ein. So for example, we know that if we've got something like this, do something straightforward like this. We have 1, 2, 3, 4 carbons, so we know that's going to be some kind of bute. And because they're all single bonded, it's going to be butane. And I think as far as we got was pretty much just saying, okay, what if we have like a C double bonded to another C, like this? This is a double bond. We know that because there's 2 carbons, it's F. And then the double bond made it an ene. If it had been a triple bond, let's just do it for fun, we would have called this eth. Right, we didn't get much farther than that. So let's go ahead and continue on with this knowledge and learn a little more nomenclature. All right, so the base, the pentane here, is something we ought to be pretty comfortable with. It's got 5 carbons, they're all single bonded, pentane, that you should know. Now, what happens when we add substituents or little parts, things kind of coming off the main chain? So what you want to do, step number 1, is find the longest chain. We're gonna, number 2, ID the substituents, and 3, put it together. So even though you have the names given to you here, let's kind of walk through how we would have named each of these, like if you didn't know. So I'll do something like this. Okay, so this first one, again, there are 5 carbons, single bonded, we would have known that's pentane, but let's go over here. So step number 1, you want to find the longest chain. So if I go from here to here to here to here, that's 4 carbons long. I don't see anything else that's going to provide me with 5 carbons, but you could go from here to here to here to here, and you would get the exact same name, by the way, if you did it this way versus if you did it that way. In fact, I encourage you to go ahead and do that. Because most of you want to go this way, let's do this way. Let's go crazy here. It's crazy. So that's going to be our parent chain. And again, that's 1, 2, 3, 4 carbons. They're all single bonded. So this is going to be some sort of butane. The next thing you want to do is look at the things coming off of it. ID the substituents. So now we're right here. The only things coming off of it I see is this one. It's got a single carbon, so this would be considered a methyl group. If there had been 2 carbons, it would have been an ethyl. 3 carbons, it would have been a propyl. So hopefully you kind of see where that's coming, or where that's going. So we got a methyl group right here. And the next thing is you want to number the carbons. So when we number the carbons, we want to make sure that the substituents are in the lowest number. So if I number the carbon here, 1, 2, 3, 4, this is going to be on a 2. If I had done the opposite direction, if I had labeled it 1, 2, 3, 4, the methyl would have ended up on a 3. We don't want a 3 because 2 is lower. So we want to start with the number. Whatever's going to give us the lowest number for the substituent is where you want to start. So we're going to start 1, 2, 3, 4. This is a 2-methyl. So we write 2-methyl and then butane. That's it. We put it all together, and that's why this is 2-methyl butane. All right, when we do this one, first, find the longest chain. 1, 2, 3, 1, 2, 3, 1, 2, 3. You could go crazy here. Let's go ahead and do what looks like kind of the most normal one in this case. Boom, boom. Now, once we've found the longest chain, we can identify the substituents. I see this one and this one, which looks like 2 methyl groups. All right, and then because it doesn't matter which way you label it, so you could start 1, 2, 3, or 1, 2, 3, you'll get the same number no matter what. So if I do 1, 2, 3, it's gonna fall on the 2. I just realized I'm using a green pen and I don't know why. Let me see if I have a better thing for you guys here, so you can see it a little better. I know green pens aren't the easiest thing to see. But because we have a 1, 2, 3, and there's 2 methyls on there, we are going to call it 2,2, because there's 2 of them, dimethyl. If there had been 3 methyls, we would have called it tri. If there had been 4, it wouldn't be correct. So 1, 2 methyls. So again, we call it 2, 2 dimethylpropane. All right, let's go ahead and name this sucker. I tell you it's your turn, you will in class. Step number 1, find the longest parent chain. So you could start a million ways. You could say 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, etc. There's a lot of different ways, but eventually you get a feel for the fact that I see 7. 1, 2, 3, 4, 5, 6, 7. So that's going to be my main parent chain that I circle. In other words, this is a heptane. Hept for the 7, ane because they're singly bonded, and now when we go to number them, if I start here and say 1, 2, 3, I don't hit something until I get to number 3. But if I go the other way, 1, 2, I hit something at 2. That's why we're going to name it this way. 1, 2, 3, 4, 5, 6, 7. All right, I hope you agree. I see 1, 2, 3 of those things. 1, 2, 3 methyls. So I'm going to call this thing 2, 4, 5 dash tri methylheptane, because again there's 3 methyl groups. Okay, there are some common names of alkyl groups that you'll be using. Most of this we use kind of standard names, but there are some common names that we're going to kind of memorize. We already know propyl, or methyl, propyl, butyl, but then we see something here, this isobutyl. It kind of looks like a Y, but then it's got these extra carbons here and here. So it has a total of 1, 2, 3 carbons and attached to something else. So this would be considered, or 1, 2, 3, 4 carbons attached to something else. So this would be considered isobutyl, as opposed to isopropyl. It doesn't have this extra carbon right there. Whoop. So ethyl, isopropyl looks like a Y. I don't really like the order that they did it, but I guess I see they're like here. Here are the butyls, there are the propyls, and there are the methyls. It does kind of label them 1, 2, 3, 4, 5, 6, 7, 8. All right, anyways, let's see if we can put that into action on this one. So step number 1, you want to make sure you can find the longest parent chain. So you can start up here, maybe 1, 2, 3, 4, 5, 6, 7, as opposed to 1, 2, 3, 4, 5, 6, 7, 8, 9. I see 9. I don't think there's anything longer than that, so I'm going to circle this 9. Find the things that come off of it. And now here's where we're going to run into some problems. So it's really important maybe to break this down. You know what I'm going to do? I'm going to do the first step I normally do. I found 9, so I'm going to write nonane. Nonane, telling me there's 9, and they're all singly bonded. All right, now I'm going to start looking at these substituents. There can be so many, it's almost best to label them first because you're gonna have to end up alphabetizing them. What I mean by that is, let's find the numbers. I'm gonna start my numbering here because I run into this first, as opposed to if I'd gone this way, I would taken me several carbons before I got to this. So I'm gonna say 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3. On my third one, I've got a 3 dash methyl. All right, and over here on my 5th one, I have this thing, which is considered what we call a tert butyl. See, it's got this carbon right here with 3 carbons hanging off of it. This is a tert butyl, and again, that's at 5. Tert butyl. It's got a dash between it. Okay, so we got a 5 tert butyl and a 3 methyl, and we want to put them together. Now, generally, you alphabetize everything. You don't put them in order of their numbers, you put them alphabetically. But we're going to run into a problem because when you have tert and sec, you ignore them alphabetically. Iso's cool. Iso, you see the I, but tert and sec, you don't. And so I'm going to alphabetize them based on this B and that M. So what comes first, the B or the M? Hopefully you agree that B comes first, and that's why this is 5 dash tert dash butyl, comma, 3 methyl, and then I'll move the nonane over here, but it was good to remember, nonane. Okay, so again, make sure that these are alphabetized. If there were iso here, if it were isobutyl or isopropyl, we would alphabetize it with the I. In this case, we just ignore the tert in the set. All right. Let's do one more example. So, whew, this one looks like fun. Oh, I like this one a lot. Okay, cool. Exciting. All right, let's go ahead and find the longest chain. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Lots of 10s. Let's go ahead and circle any of the 10 carbons. Again, you could have come up this way and you would have gotten the exact same molecule. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. I'm cool with it. All right, so when we are numbering, we want the number to go here. This is going to be 2 because that's the first one I run into. If you ever have a situation, by the way, and I wish I had an example problem of this, where you run into one that on both sides. So let's say you run into one here and you were to run into one here and you didn't know which one to do. You put the lowest number on the lower alphabet side. So for example, if you had ethyl here and a methyl here, you would start with a 2 over here with the ethyl because it's lower in the alphabet. So you keep low numbers with low alphabet things if you're in a situation where it doesn't matter which way you go to number. Okay, so we got 1, 2, I'll provide an example for that in class, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so let's list them all out. First, we know that this is a decane. Let's write that sucker over there because we got 10. Now, let's go through each one. I see it here, we got a 2-methyl. Right here, we have a 3, it's got 2 carbons on it, so this is a 3-ethyl. 4, 5. On 5, I have this thing. Do you remember that thing is called a sec-butyl? Okay, and then 6, 7. On 7, I have another methyl. When you have 2 methyls, you will combine them to make a dimethyl. By the way, dyes are also ignored alphabetically. Di, tri, tetra, etc. So, so this is going to become a 2, 7 dimethyl, these two. And we still have this and this to order. All right, so we're looking at the M here, the E here, and the B here to determine which one to go first. That B comes first alphabetically, so my first part is going to be the 5. Sec-butyl. Okay, so we've taken care of that one, comma. After the B comes an E, 3-ethyl, comma. After the E comes the M, 2, 7, just like I have it written here, dash dimethyl. And then last but not least, we can't forget the decane. Yay! Wasn't that fun, you guys? I thought that was awesome. All right, so this is how we would name that beautiful molecule right there. All right, cycloalkanes is very similar. I'm not going to go too much into it, so I just provided this kind of walkthrough thing. So if you have just one substituent, you don't need to number it at all. So like, for example, here we had this ethyl group coming off of this cyclobutane. There's 4 carbons in a ring, and that's why it's called just ethyl cyclobutane. Over here, whenever you have like 2 things coming off of it, you have to name the numbers. Just make sure you name them as close together. You don't want to go like 1, 2, 3, 4, 5. You want to go 1, 2, 3, so you keep the numbers as low as possible, which is kind of your goal in the other situation too, right? So 1, 2, 3, this would have 1 It's got the sec-butyl, it's got the 3-methyl, and of course butyl comes first alphabetically, the B comes before the M, and that's why you put 1 sec-butyl. All right. Now, also noting, also an important note, and this kind of goes to the example problem I was talking about earlier that I wish I'd had, is this is sec-butyl, right? And this is methyl. I could have just as easily started with a 1 here and then gone 2 to 3, but we want to keep all rules consistent, right? So that you don't get 2 names of the same molecule. So that's why you started with the 1, because this one had a B, it came first alphabetically, it got the 1, then a 2, then the 3 here. So this is because this got 1 because it is alphabetically first. Alphabetically first. Okay, so that got 1 because it's alphabetically first. All right, here we've got this. Remember to give the second group. So, oh yeah, kind of the same thing. You want to keep these as close together when you're numbering. You don't want to go 1, 2, 3, 4, 5, 6. You want to go 1, 2. And then here, it's the same situation. Make sure you're numbering as close as you can together. 1, 2, 3, 4, and not 1, 2, 3, 4, 5. You want the lowest order of numbers, not the higher one. Okay, now we're on to Newman projections. So acyclic alkanes. Acyclic alkanes are kind of cool because they rotate, they spin. All right, and we're gonna spend a lot of time here. Before we get too much into this, I want to kind of talk about how they spin. So it's funny, I have this sitting here, and I wish I had 2 of them because I could do so many demonstrations with this. So I might bring this back in here in a little bit. But essentially, imagine if you had 2 of these, and this was a carbon right here and another carbon right here, they could spin. They can spin in opposite directions, or the same direction, and they can rotate. As opposed to if you have, notice this says alkanes, that's for a very specific reason. If you had alkenes, let me get another pen. And let's say you had a carbon here and a carbon here and it was double bonded like this, you couldn't spin it because the bonds would get twisted up. It's like having a rope and trying to spin, it wouldn't go. So this only works for alkanes, single bonded carbon to carbon bonds. All right, double bonds don't work. Or triple bonds definitely don't work. Okay, so so when you have a carbon bond like this, in fact, I'm gonna pull this thing off. I got one. I got this. Okay. There we go. So I've got this thing kind of put right here, and just imagine I have hydrogens on here. I don't, because they're just annoying to take on and off, but imagine I have hydrogens, and this thing can essentially spin around like this. Whee! No, the opposite direction too. Whee, it's so fun. Okay, in the eclipsed conformation, these things are lined up. So can you see that this hydrogen directly behind it is there, that one's there, that one's there. This is called eclipse. They're lined up, right? They're beautiful, they sit perfect. This is actually a high energy conformation. This is unhappy in this conformation actually. But then we have a staggered conformation where one of them just goes whoop, it flips, just like that. And now there's no, what we call a hindrance. This hydrogen is between these 2 hydrogens, and they're much happier this way. This is actually a much lower energy state because they're not pushing against each other, right? If you have a hydrogen here and a hydrogen here, they're both positively charged things, so they want to push away. So this is a much more stable conformation. This is called the staggered conformation. And so it's at an angle. All right, so kind of like we just showed you, this is the eclipse. All the carbon-hydrogen bonds are aligned, and staggered is they bisect each one. So get used to that terminology. You'll be using it a lot. Okay, so it says drawing Newman projection, so we're going to do something called a Newman projection. Even though it kind of walks you through it pretty well, we're going to go ahead and do it with this thing anyways. Okay, so we have currently, in fact, go ahead and do a staggered conformation. It makes it a little easier to see. Okay, so we currently have this carbon-carbon double bond, or carbon-carbon single bond. We want to make something called a Newman projection. So what you do is you draw a circle, and you just want to project what this would look like. So in the front, I hope you agree, there's a hydrogen, and a hydrogen. So you would go like this: hydrogen, hydrogen, hydrogen. And then in the back, can you see that we've got another hydrogen, hydrogen, hydrogen staggered? So in the back, you would draw hydrogen, hydrogen, hydrogen. Notice that in the back, you don't have lines connecting all the way to the center, but only in the front carbon do you represent it with the lines. So I hope that makes some sense, and that's how you draw a Newman projection. Now, if I were to stagger this, let's go ahead and do that. Let's draw what that would look like. We'd have a circle. And in the front, we got the hydrogen, hydrogen, hydrogen. And then just behind this hydrogen is another one. So what you could do is you could draw like this. And this is how they do it. Usually actually it'd been on this side. My bad. Let's not put it there. Just to show you that it's directly behind, there's another hydrogen peeking through. And you could have just as easily gone on the other side. It wouldn't matter. All right, and here they show you just that. We got a staggered conformation where they're staggered, and eclipsed conformation where they're together. Remember, this ends up being the lower energy conformation. This is a higher energy conformation. We'll get really into that in the next lecture. But mainly, I just want you to get comfortable doing Newman projections so we can have an idea of what things look like. All right, so here it says, convert each representation into a Newman projection around the indicated bond. Okay, so I'm going to go ahead and throw bromine. It's a little bigger. I'm going to throw bromine on here and chlorine on here. Like that. And some of you might be able to visualize this very quickly, very easily. I encourage you to do that. And for the CH3, I don't know if you see in the CH3 and CH3 in the back, there's another C. I'm going to do this as a CH3 and this as a CH3. All right, so the green's the chlorine. The yellow is a bromine. The nothing is a hydrogen. Back here I got a nothing, and I got a CH3 and a CH3. Okay, and it wants us to draw it. Now it looks to me like they're all in this trigonal pyramidal conformation. So we got one up, one boom, 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 and boom, boom, boom. They're all tetrahedral is really what they are, but I'm talking about this part would be like trigonal pyramidal. All right, so all we do is draw it. It's that straightforward. So we'll do our circle. All right, we know down here is the bromine. Up here at the top is a chlorine. And then right here is the hydrogen. So bromine, chlorine, hydrogen, bromine, chlorine, hydrogen, and then you just ask yourself what's behind. Well, again, they're all in the same exact location, so this would be what we consider eclipsed. And so behind it, we have a hydrogen, or behind it we have, a methyl group, CH3. Here we have a CH3. And here we had a hydrogen. Okay, and that would be the Newman projection of this thing or this thing. They're the same one. All right, great. Now on this one, let's move things around a little bit. It's not as straightforward, but I really encourage you to try to visualize this in your head without using models. Really make your mind work and picture moving this molecule around and what it would look like, because we want to be able to look at it, if this is our eye, this way. We want to be able to visualize it going this way through this carbon-carbon bond. So in order to do that, you kind of have to shift this up 90 degrees in your mind. So you have to shift this molecule up. If I shifted this molecule up, remember this one, this wedge is coming out at us. So if you shift it 90 degrees, now it's in the plane this way. And this hydrogen, which is going into the plane, if you shift it now 90 degrees, now it's going this way. So picture really, really work hard at picturing this. If it's not as intuitive, let's put it into a model kit here. Okay, so this back carbon still has a CH3 and a CH3. I'm gonna go ahead and keep those. I'm gonna move this one up here though. Okay, so like this back one, you have one that's going in and one that's in the plane, much like this is right now. So I'm looking at this carbon. This CH3 is in the plane, this CH3 is going into the paper, and this hydrogen is coming out of the paper, just like this. Okay. Over here, we have an H. I gotta spin it in order to get this right, and that should tell you something about the conformation. And this one, I have an H that's going into the paper. I have this CH3 thing that's coming out, so I'm just gonna put a yellow to kind of indicate that the ethyl group there. And then the hydrogen is right there. And it wants us to draw this conformation. So again, when I say shift it 90 degrees to the right, I mean go like that. So we were here, and this CH3 is right there. I was going in, and I want you to shift it 90 degrees up. And what you'll find is you've got this staggered conformation of a thing. So let's go ahead and draw it. Once you have this kind of pictured in your head, it makes it a lot more simple to draw. Okay, so right here, going up on our right in the front, we've got this CH2, CH3. We have a hydrogen here and a hydrogen here. Then down here, we have a CH3. Down here, we had a hydrogen, and up here, we had a CH3. You are welcome to bring model kits to class if this helps. The problem is on an exam, you're gonna wanna be able to just flip it over in your mind and draw it out. But model kits do help us get an idea of what it should be. So, all right, so that gives us a general introduction into drawing Newman projections. You'll be doing it quite a bit, and again, we'll be talking about the energetics of it here shortly in the other second half of chapter 4. All right, have a great day.